So good morning to everyone. Today we are going to understand Boltzmann Transport Equation. Okay. So this Boltzmann Transport Equation is concerned with the determination of steady state distribution function of the system under external fields. Okay. So before going to understand this definition, first of all let's clear few of the term. Okay. Say we have a system, say 3D system, 3-dimensional system, or 2-dimensional system, 1-dimensional system. Okay. Just a system. So there in that system there will be electrons. Okay. So those electrons will be distributed, and the distribution uh, is followed by Fermi-Dirac distribution function. Okay. How these electrons are distributed is followed by Fermi-Dirac distribution function. Okay. So uh, so with the help of that Fermi-Dirac distribution function we can calculate uh, this average energy of our electronic system, that our three-dimensional system, how much electrons they are, what is the average energy, we can calculate this. Okay. Basically this dE act as a density of a state, that is how many states are available for a particular energy range E and E plus dE. Okay. And this AP, this is a Fermi Dirac distribution which acts like a something like uh, total number of available states by number of available states by total number of states. Okay. So this total number of states get cancelled with this dE density of state, the total number of available states. So multiplying this dE and Fe together give us number of available state for a given temperature. So this dE Fe, okay, this gives us number of states available for a given temperature. Okay. And we are doing average, so E and dE. So in this way we get this average energy, and many kind of properties thermodynamic properties we can obtain with the help of this Fermi-Dirac distribution function. Okay. Now so that's the importance of this Fermi-Dirac distribution function. Basically we had considered a three-dimensional electronic gas system. Okay. And and that's like we had calculate the system average kinetic energy, and we can calculate number of uh, how many number of electrons uh, available in our system. So in this way this Fermi-Dirac distribution is important, and density which is nothing but it is just an number of states, total number of states, that is for a particular energy range. Okay. And this Fe is just a ratio, that is uh, number of available state by total number of states. Okay. And that number of available state depend upon temperature, it varies if we vary temperature. Okay. So this both together gives us a number of available state for a given temperature. Okay. So that's the importance of Fermi-Dirac distribution. Now back to our definition that we had studied at the earlier of our discussion. That is, the Boltzmann Transport Equation is concerned with the determination of the steady state distribution function of the system under external field. So what will be happen to the Fermi-Dirac distribution function if we are going to apply some kind of external field, say electric field or magnetic field, or our system is subjected to an temperature gradient. Okay. So such kind of external fields, if we are subject to our system, then how our Fermi-Dirac distribution changes. So now back to our definition. The Boltzmann transport equation is concerned with the determination of, okay, a steady state distribution function. Okay. So when we apply external field, okay, under the influence of external field, after a few moment our system comes to a steady state. Okay. So determination of the steady state distribution function. Okay. So it's under that steady state, what will be the our distribution function of the system under external field. So simply we can say that Boltzmann transport equation is concerned with the determination of the steady state distribution function. That is, we are going to obtain a distribution function under a steady state, and that steady state is basically due to this external field. So under the influence of external field, and after a few moment of time when our system come to a steady state, what will be the distribution function? That's our main and that's our main target, to obtain this distribution function when we apply some kind of external field. Okay, and that distribution function for is nothing but a Fermi Dirac distribution function if we are considering an electronic system. And basically I'm discussing uh, I'm just considering at the beginning only that our particle is an electronic particle for clear visualization. Okay, so this is our distribution function. Basically when there is not any kind of external field, then it will be totally Fermi Dirac distribution function. Okay, now we are going to see how this Fermi Dirac distribution, what are the modification that will be obtained after applying external field. Okay, so 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 now let's apply a deep variation, that is we are going to apply some kind of external field. Okay, to our system, to our three-dimensional system, or whatever we would consider three-dimensional system, but we are treating the situation generally, so we can say two-dimensional also, one-dimensional also. Okay, so this is our tree variation, and we are going to apply some kind of external field. Okay, now let us consider an electron in our system which is at position coordinate xyz, and at the position coordinate it has velocity vx, vy, and vz. Okay, so under the influence of an electric field, that electron shifts to this coordinate x minus bx dt, y minus by dt, z minus by dt, and its velocity coordinate changes follows: vx minus alpha x dt, vy minus alpha by dt, vz minus alpha z dt. Okay, at time t, and at time dt it was at this mm, at this coordinate. Okay, and at time t, this at t plus dt it is at this coordinate, and time t it is at this coordinate. Okay, but this changing coordinate basically happens under the influence of external field. So what will be the changes in our distribution function? Okay, so this is our distribution function basically at time t plus dt. So after time t, its coordinate change to this. Okay, so just let's see what will be the changes in our distribution function under the influence of external field. Okay, so let me clear first of all once more again. I think I had confused you. Mm, we are considering a system. Okay, in our system there are electrons. Okay, now say among those electrons I had considered one electron, its position coordinate x y z, and that's like its velocity coordinate is vx, vy, vz. Okay, now and say this that electron coordinate, mm, this x y z comma bx, vy, vz. Okay, at time t plus dt. So after time t, its coordinate change as follows. Okay, so basically this coordinate changes basically because of due to under the influence of external field. The electron changes its coordinate under the influence of external field. Okay, so this is our distribution function. Okay, now if we apply some kind of external field, then this coordinate changes to this. Okay, so our distribution function also changes. Okay, under the influence of external field. Okay, so what will be the changes? And basically this change is due to drift variation, that is external field. Okay, so let's check what will be the variation. So this is our Fermi Dirac distribution. Sorry, this is our distribution function under the influence of external field. Changes are these. Okay, so this dt is very small, so we can expand by Taylor series expansion, and after expanding we'll obtain this. Okay, and this df by dt, then we are right subject to the drift. Okay, so our distribution function changes in this way in the under the influence of an external field. Okay, now uh, let's discuss collision variation. Okay,